Hello, ladies and gentlemen. My name is Aleksey Burtsev, and the theme of my presentation is the mathematical model of a multi-layer wall of a plate heat exchanger. Problems: high temperature of exhaust gases and ventilation emissions, environmental safety of the adjacent territory, protection of steel surfaces of ventilation and boiler units from corrosion resulting from condensation of emissions. Emissions of harmful substances into the environment, increase in fuel consumption. Decision: the use of recuperators, plate heat exchangers, and devices for deep utilization of waste gas heat and ventilation emissions. Aims and objective of the study. The aim of the work is to study the increase in efficiency and integrated heat recovery of waste gases and ventilation emissions in a plate heat exchanger with multi-layer plates due to turbulence of flows with the associated production of thermoelectricity and the determination of parametric relationships between the physical parameters of the process and the generated thermal EMF. The aims is achieved by solving the following tasks: a theoretical study of the intensification of heat transfer through the use of turbulators, an experimental study to identify the parametric relationships of the process of increasing the heat transfer coefficient with the associated production of thermoelectricity due to turbulization of ventilation emission flows. Analytical study of the influence of heat and mass transfer processes on the intensity of heat transfer. Drawing up the theoretical foundation of the parametric connection of the intensification of the heat transfer coefficient with associated production of thermoelectricity in cross heat exchange and the technologically of turbulization of flows through the use of heat exchange surfaces in the forms of swirls. Descriptions of the process of interaction, of condensation of water vapor and its connection with the use of heat exchange surfaces in the form of swirls as a result of turbulence and a decrease in the temperature of the flue gas through and ventilation emissions. Constructions of a mathematical model of the parametric relationships of the process of intensification of the heat transfer coefficient with the thermal EMF during cross heat and mass transfer and the technologically of turbulization of ventilation emissions flows as a result of changes in the shape and area of heat exchange, taking into account the condensation of water vapor. To achieve the above objectives, an experimental setup, figure 1a, consisting of two blocks was developed. The blocks are a complex multi-layer plate heat exchanger and an absorber. The multi-layer plate heat exchanger block is made in the form of ribbed heat conducting sections into which semiconductor Peltier thermionic elements are mounted to intensify the heat transfer process. Cylindrical turbulators were installed on the ribs. Here you can see these pictures. On this slide, you can see in other pictures, figure 2. On this slide, you can see the experimental results. Air heated in the heater was used as a heat carrier. Air taken by a fan from the laboratory room was used as a working medium. Experiments on the study of heat transfer with counterflow in the thermal selection were carried out for the modes consisting of a number of fixed velocities and airflow rates using the experimental setup. A number of experimental studies were carried out using the multilayer plate heat exchanger installation shown in tables 1, 2, and 3. Discussion of experimental data. As can be seen from these experiments, the installation of turbulators significantly intensified the heat transfer process by increasing the temperature difference between the cold and hot sides from 28 degrees to 30.5 degrees. Simultaneously, there is an increase in electricity generation, both per unit on thermoelectric element and the installation as a whole. For example, the total voltage of the installation without turbulators and thermal gaskets was 24. After the installation of gaskets, voltage increased by 2.5 times up to 60. In installed turbulators contributed to its increase up to 200 microvolts. The installation of thermal gaskets improved the contact between the semiconductor peltier elements and the cooling radiators, which made it possible to increase temperature difference and as a result electricity generated. In addition, the hot air temperatures at the outlet of the heat exchanger decreased significantly from 47 degrees to 29 degrees. And as a result, the temperatures of cold air entering the laboratory room increased from 21 to 24 degrees. At the same time, a decrease in the hot flow rate from 2 and 4 to 1 and 9 is noted, which takes place due to the increased aerodynamic resistance. You can see it at the figure 3 pressure drop graphic. Simulation of flows in experimental setup. In order to simulate the flows inside the unit, experimental installation, a computer model shown in the figures 4A and 4B was developed. We're used to Solidworks software with the flow simulation package version 2090. The purpose of the simulation was to determine the areas of turbulence and vertically of flows along the direction of hot and cold air movement. Here you can see flows turbulization simulation, cold air flow, and another picture, hot air flow. Here you can see turbulence zones and highlighted in yellow. vertically areas of cold flow are marked in blue. On the figure 7, the diagram of the scale of turbulence. The curves of the scale of turbulence, which characterize the effective size of the moving gas volumes, in which at a given time interval all the particles have the same movement velocities, shown in blue. In this case, some volumes of gas, in addition to the average velocity, have disordered, rapidly changing additional velocities. Pulsation velocities shown in red. For a turbulent boundary layer under the previously adopted restrictions, the equations of energy, motion, and continuity can be written as follows. You can see this here on this slide. Here you can see the diagram of the turbulent velocity coefficient. Turbulent velocity coefficient, which characterizes the superposition of the pulsing motion, shown in red, on the average motion, shown in blue. Here you can see the diagram of turbulence energy. Average kinetic energy per unit mass of the flow associated with vertically in the turbulent flow, characterized by a change in the RMS velocity pulsations, as well as by the degree of turbulence. Here you can see the diagram of turbulence dissipation. Conclusion. The obtained computer simulation data, the diagrams of the scale of turbulence, figure 7, and the turbulence velocity coefficient, in particle, indicate that in the progress of movement, part of the flow has the same velocities, while some volumes of gas have disordered, rapidly changing additional velocities. The so-called pulsation nature of the flow due to the increase in relation to flow, the velocity of the averaged movement due to the use of turbulators in the form of cylindrical surfaces. The diagram of the kinetic energy of the turbulent flow, the figure 9, which characterizes the average kinetic energy due to the change in the RMS velocity fluctuations, indicates a gradual disposition of turbulence on figure 10 as a result of the transition of the flow energy into heat due to thermal conductivity. As a result of the study, mathematical equation for the dependence of turbulent heat transfer to the quantity of motion were obtained, which will subsequently serve in solving differential equation of convective heat transfer and determining the optimal method for intensifying the coefficient of heat transfer through a ribbed wall with cylindrical swirls installed